for being here. My talk today is a little bit different than the previous ones because today I'm not going to talk to you about my work. Instead, I would like to give you a brief introduction to what is called Levy of stable distributions. So this is not my work, but this is a tool that I use in my day-to-day work. So by distribution, I mean a statistical distribution. So this is a mathematical object, right? So let me start. Okay. So in today's talk, first of all, I will try to convince you that the world that in which we live in is not normal. Then I would like to generalize everything. So I would like to generalize or to tell you about the generalization of the central limit theorem. Then I will introduce what are the Levy stable distributions, where do we find them, and how do we use them. And finally, some usages I give to them, right? So first of all, the word is not normal. By this, okay, as you can see, normal is written like this because with normal, I mean Gaussian, right? And the point is that from textbooks, when we study in the school, in high school or anything, our teachers used to tell us that whenever you have a statistical variable, if you take the sum of that variable will tend to be a Gaussian, will tend to have a Gaussian distribution. So we grow thinking that everything in the world tends to a Gaussian distribution, but that is not always true, and I want to convince you about that. The point is that in the real world, the physical systems that we can find in nature are much more complex than any model that you can find in a textbook, right? Well, in basic textbooks. So, as I told you, we grow thinking that everything in the nature tends to a Gaussian distribution, and that is governed by the central limit theorem. This is a very basic theorem that we have all learned in high school, or maybe in the bachelor's, and it's a very powerful tool also. In mathematical language, it is you can describe it as follows. If you have random variables that are independent and identically distributed, and you take the sum of many of those variables, then the distribution of that sum is going to be a Gaussian distribution. And it doesn't matter what is the distribution of the number that you are taking. For example, you can roll a dice, and you well, not one dice, but many dices, and then you sum the result of all the dices, and you take the count or the sum of those dices, and if you plot the distribution of that experiment, then you will see a Gaussian if you repeat this experiment many times. And that will happen for many other examples. For example, if you ask the height of everybody in this room, and if we were many of us, then the distribution will be Gaussian, and so on and so forth. So this is what we all of that everybody of us know. But there is a catch, because in order for the central limit theorem to work, you need something very essential. You need that the variance and the mean of that variable that you are summing is finite, right? So in other words, you need that the first moment and the second moment of your distribution is finite. The point is that in nature, this doesn't happen very often, because in nature, if you are studying any phenomena, it is very likely that you will find outliers. So outliers are events that are not that do not follow the rule of the rest of the distribution, right? And you cannot ignore them. You cannot just think that, okay, this point doesn't exist and we're good. No, you cannot ignore them. So these outliers essentially mean that the variance and the mean of your distribution to real distribution is not finite. So whenever this happens, then you say that the distribution have heavy tails, or in other words, extreme outliers. If this happens, then the central limit theorem fails. It doesn't longer apply to whatever you are studying. So this is the point that in nature, this is very likely to happen, right? So then what happens there? What can we do if we encounter these kind of systems? Well, I have an example here, for example. You can see this little plot. Here I'm showing you two different distributions. One is a bell curve or a Gaussian distribution, the blue one, and the other is a Cauchy distribution. And the thing is that if you have a system that follows this Cauchy distribution, and if you take many, if you have a very large sample set, for example, a million sample set of variables that have a Cauchy distribution, you will encounter that the sum of those variables is not a Gaussian. It doesn't matter how many variables of them you take into account, it will never tend to be a Gaussian. Instead, it will remain as a Cauchy distribution. So there is something happening here because, as I told you, we grow knowing that whenever you sum many variables, they will tend to be a Gaussian. But I told you already that if this is not fulfilled, then that will not happen. And the Cauchy distribution is one of those examples. So the thing is that these finite variance assumptions break down in many phenomena in the nature. For example, whenever you study turbulence, or whenever you have anomalous diffusion, or plasma confinement, laser cooling, and many other phenomena, you will observe that these systems are characterized by scale invariance and fractality. So if your system is scale invariance and your system has fractality, then the finite variance assumptions will break down. If you don't have finite variance, central limit theorem does not longer work, and then the distribution of those variables is not a Gaussian distribution. So the fluctuations in these phenomena are not bounded by exponential decay. Instead, they exhibit heavy power tails. So the first takeaway of this talk is that the world in its true complexity is not normal. Yes? Yeah.
What do you mean by scale invariance here? What do you mean by scale invariance?
Yes.
Because you are separating the scale invariance with fractality.
Yes.
Here.
Yeah.
That means I will imagine that you are talking about some scale invariance which is not related to fractal.
Well, I'm not sure about that because I don't know if whenever you have a system that is a scale invariance, that system is a fractal. I'm not sure about that.
But scale invariance, you are talking about real space or scale invariance in real space, or your Fourier space, in which space you are talking?
No, in real space.
Scale invariance in real space.
Yes, because if you have a scale invariance in real space, that means that you don't have a finite variance. Right?
Okay, that's the convenience you are talking.
Yes.
And you are not sure that you are differentiating it with fractality only.
Yes, I'm not sure about that. Okay, so the world in its true complexity is not normal. So let us generalize everything and let us talk about then what happened. If we don't have a Gaussian distribution, then what do we have? Okay, so let me present you, first of all, what are the Levy alpha stable distributions. This person here is the French mathematician Paul Levy. Paul Levy showed that whenever you have independently distributed variables, just as before, these x, and if those variables doesn't have finite variance, if you take the sum of those variables, you will find that this sum converges to some distribution. But of course, it will not converge to the Gaussian distribution because the variance is not finite. But Levy showed that the distribution that this sum have is one of a family of distribution called Levy alpha stable distributions. So Levy alpha stable distribution is a whole family. It's not one distribution, but a family characterized mainly by the stability parameter. The stability parameter is alpha. Actually, alpha is there in the name of the distributions. And alpha can have any value between 0 and 2 inclusive. So you can see that you can have many different distributions in this family. And that's what we call the generalized central limit theorem. It's very related to the central limit theorem, but instead of saying that the sum have a Gaussian distribution, you say that the sum have a stable distribution. Which distribution? Well, it depends on the distribution of the individual variables, right? And in this whole family of distribution, there are three famous cases, which I show you here. When alpha is equal to 2, we recover the Gaussian, right? But in general, for any value of alpha, we don't have analytical expressions for these distributions, only for these three: the Gaussian, the Cauchy distribution when alpha is equal to 1, and the also so-called Levy distribution for alpha 1/2. But in general, for any alpha, you do not have analytical expressions. Do you have a question? No? Okay. So this is the formal definition of the Levy of stable distributions. And now let me tell you in practice, how do we handle this kind of distributions? Well, we define them via their characteristic function, because as I already told you, there is in general no analytic description for the probability density function, but we do have the characteristic function. It's just the expectation value of this exponential, or you can write it explicitly as I did here. So you can see that these distributions are characterized by 4 parameters. I already told you that the most important is the stability parameter, alpha. There are all other 3 parameters, which are the usual for any distribution. You have mu, that is the center of the distribution. You have c, that is the scale of the distribution. And you have beta, which is the skewedness. All right. So here below, I also presenting you 2 different plots. Because a part of this definition of stable distributions, I have to tell you that there are different parametrizations. And with these parametrizations, you can distinguish between 2 big family or 2 big subsets of distributions, which are symmetric distributions and asymmetric distributions. So the symmetric ones, here I'm plotting different PDFs for different alphas. You can see that all of them are symmetric in 0, because I put mu 0 here, of course. And as you get alpha bigger and bigger, up to 2, this will converge to the Gaussian. But while alpha is smaller than 2, all these distributions doesn't have a variance. The variance diverges. And when alpha is less than 1, also the mean diverges. So we say that these distributions are heavy-tailed distributions, because the tail of the distribution is not, well, it will continue and continue, so on and so forth. And that heavy tails are the responsible of you to have these outliers, okay? So the first important characteristic of the distribution is that whenever alpha is less than 2, you don't have variance, and whenever alpha is less than 1, you don't have mean. Okay, those are the symmetric ones. Then you have the asymmetric ones that have the characteristic that also, whenever alpha is less than 1, all these distributions have support on the positive real axis. As long as alpha is equal to 1 or higher, you can see here, this purple is 1, it does have some negative contribution. But as long as alpha is less than 1, you have support only on the real axis. Okay, so this is more, this kind of distributions are more likely to be the ones that describe phenomena in the nature, because, well, it depends on your system, but it is important to say that we have these 2 options, right? Symmetric and asymmetric. So here I'm just showing you 3 different histograms of the 3 analytic cases that we know. This is the Gaussian distribution, so alpha equals 2. I don't know if it's visible to you, but here I have histograms, and the envelope of the histogram has a solid line. That solid line is the analytic expression, right? So this is a Gaussian, this is a Cauchy distribution. Remember that the Cauchy distribution is a Lorentzian, and this is the Levy distribution. But as I told you, we only have analytic expressions for these 3, but I already showed you different plots for different distributions, even though there is no analytical expression for these distributions. So the next question is, how do we handle them? How do we work with them numerically, for example? How can I get a set of random variables that follow a stable distribution?
So I'm maybe confused, but so you have an analytic expression for the characteristic function, and you cannot just simply Fourier transform back from that?
For sure, you can do that, but the point is that, I mean, analytically, you cannot. So there is no closed form.
There's no closed form for the inverse transformation of that.
Yes, exactly. Okay. And if you want to work with it numerically, it's going to be very expensive, computationally expensive to do it in that way. So that is what I want to tell you. How do I get these plots? Well, it turns out that I will skip a little bit this. This is a recipe which I call the CMS algorithm. So it came from this paper from 2012. And in this paper, these three persons give a very elegant and very useful and well-applied algorithm to generate stable distributions. So this is the recipe for numerically got the distributions, right? And this is what you have to do. Okay. Now I want to tell you where do we find them. I already told you that in the nature you expect to don't have Gaussian distributions, but how can I tell you that this is true, right? Or where you can find it. So for example, here I'm showing you two different plots. You may recognize them, at least the first one. This is just Brownian motion. So Brownian motion is follow central limit theorem, so there's nothing special. But there is a different pattern that is similar to the Brownian motion, but it's not the same. You can see this is something called a Levy flight. So a Levy flight is essentially something like the Brownian motion, but you have outliers. The outliers is that, for example, if you are here, the next step, instead of be some small step around your current point, is a big step, a big jump, right? So these are the outliers, and the thing here is that whenever you have Levy flights, the probability of having a really big jump is not negligible. And this is not described by the central limit theorem. So this is an example of where do you find the stable distributions. Also, in this kind of collage, I try to show you that it is very well known. I mean, it's very well documented in the literature that, for example, the patterns of the flight of many birds follow Levy flight. So they are following, or they are moving according to a stable distribution. Also, the hunting patterns of marine predators also follow stable distributions.
Do you have an example of animals not following, I mean, doing Levy distribution? So, which are not, I mean, if they move in a kind of a flock, in the case of birds or dolphins, which are all together, I mean, this happens only for single individuals in species, or, I mean, which tend to be single, or?
No, actually, in this paper of Nature, if I'm not mistaken, they study this group of, how do you call it in English, cardumen, a cardumen of fishes, and the cardumen moves following a Levy flight.
Okay.
But I don't know if that's cheating, because we know that cardumens act like one individual. So yeah, apart from that, I don't know. But I can tell you that many different phenomena in nature follow Levy flights. For example, these. Also, we can find stable distributions in the financial market. If we follow the stock market, you will see that I'm showing you here a picture. The distribution of the stock market is not a Gaussian. You see this vanished line here is a Gaussian, but this solid line is a stable distribution. These are the data. So you see that the stable distribution fits better to the data than the Gaussian. So the stock market also follows a stable distribution. Well, if you shoot light in some photonic lattices, you will expect anomalous localization. That is also because of the stable distributions. Well, there is, as I told you, many documentation in literature. So this seems to be the rule. Okay, so
May I make?
Yes, please.
So I have the feeling that I think collectivity, some kind of swaps out stable distribution phenomena and fit it more into kind of normal, because otherwise we would never seen even normal at the beginning when we started doing statistics, right? We will always see, okay, there's no mean or variance here that goes finite, but somehow when we start working on this, we work together. We're single, so kind of like the population or the collectivity. That's my feeling.
Yes.
Kind of wash out all the outlier phenomena.
So yes, yeah, I understand your comment about. I don't think so because, well, I will have to check it, but I don't think so. I have the feeling that it is not. I have the feeling that in nature you will find both. You will find something that has a distribution that has finite variance, but you will also find many examples of something that doesn't have finite variance. So that actually the takeaway of this topic is not to tell you that your teachers were wrong, but to tell you that there is something else. There is a generalization.
Yeah, I think my point is more or less like we tend, if things are going to work, or if we are going to build something upon something below, it somehow has to be kind of normal
Well,
distribution.
that's the paradigm that
If
you
it is
should.
purely random, if your process is purely random, then it's Gaussian. But if your process have how can I say, have
Yes,
some kind of
complexity
correlations,
structure in
some
the-
kind of correlations, they
Yeah,
tend
yeah,
out
yeah,
to
yeah.
meet the Levy distribution. For example, the foragers, they find out food following a Levy walk, okay, Levy flight, or like human segregation. Okay, all over. If you look at those who leave their homes,
Yes,
they're mostly like Levy
yes.
walk.
But in society, for example, once you have buildings and stuff, and running stuff around, you basically run on normal Gaussian distributions for everything.
That I will agree with you 3 months before, but now I'm not sure.
Okay.
As I told you, this is a paradigm, right? We have to know it a little bit.
Very recently, we find out some paper for large cities. Okay, if you look at the household of the more than 65 years old people, okay, they create these long range connections like a factory. Okay, but if you also those people who just start coming less than 18 years old, the household of the 18 years old, those who are staying, they also this has been seen in Lisbon, Paris, New York, those places. So that is not very clean, that work, I would say.
No, because
But they see that this kind of thing. But it's very well known for
averages and
foraging.
variances are changing in time, and
Yes.
I think it's
Yes, but this is well known for foraging problems. That's very basically the walk is very flight. For all the foraging and resource searching, okay, of the animals, that's basically. And for a long time, people try to understand why it's like.
The other thing is that you can do a lot with the normal, but probably not so much with this heavy tech.
yeah.
So all this tailored for the other.
Yes, because if you have a heavy tail, many times if you forget about the tail and cut the distribution above the tail, that look like no.
No.
That's like
I
coaching.
don't agree with that. No, it depends on the stability parameter, right? Take a look at this. These are not the same.
Yeah, but you cut it
Cut it
zero.
there.
Yeah. Look at here.
But then you rescale the variance.
I think that it depends on the stability parameter.
Yeah, I mean, if you really look, then you are.
Yes, but my point is that if you really do not do many cases, or do not do this extreme value statistic, if you do not.
No, but that's another thing, because as I told you earlier, those outliers cannot be ignored. Because if your phenomena that you're studying follows a Levy distribution, that means that you cannot ignore the outliers.
Yes, you decide.
So cutting the heavy
decide
tails.
to include the outlier, but if you do the gross statistics and if your statistics is not very nice, then you miss it.
Well, then you're doing wrong calculations.
Yes, but that has been the case for
some time.
decades.
Yeah.
That's exactly what I'm
We should do the things right. Okay, so let me continue if you agree. So I told you that this is the holy recipe. So the recipe is written here. So whenever you want to simulate a set of random variables that follow a stable distribution, this is the recipe. X is your random variable that depends on set, and set is calculated following this equation. So please don't put attention on the details. I just want to tell you that there is a recipe, there is an algorithm. Okay. So I told you where do we find the stable distributions, but I want to tell you how to use them. So this is my most recent work that has to be to localization in homogeneous media. The thing is that this is a system that is disordered, and the disorder in this system follows a levy of a stable distribution. And as long as you introduce this levy of stable distributions, it turns out that the localization phenomena, which is one of the most famous phenomena in this kind of stuff, does not longer apply. So this is a wave packet that we let evolve in our disordered media. And if we have Anderson localization, we would expect that the localization is exponential. But since we have stable distributions instead of like-tiled distributions, we observe that the localization is not longer exponential, but it's a stretched exponential. So again, I don't want to get into details. I just want to tell you that when you consider stable distributions instead of Gaussian distributions, things change. Also, another usage of stable distributions has to be with the engineering. So I told you that this work, in this work, we had an experimental part, and the experimental part was done in some photonic lattices. So we have to fabricate these photonic lattices. And the way in which we fabricate these photonic lattices was following stable distributions. And by doing this, we are able to characterize what is the localization that we get. With this, I mean that if we change the distribution we are using here, then the result is going to be different. But the important thing is that we know how different it is going to be. So we can engineer things to achieve our goals by using different stable distributions. And of course, there are some open questions that has to be with these stable distributions. Going back to this system where the disorder follow stable distributions, it turns out that if we count the density of scatterers in these models of transport and localization, whenever we have stable distributions, for the asymmetric case, the one that only has support on the real axis, in the positive real axis, we find some singularities. You can see that in this example, where the distribution was symmetric, it doesn't matter what this graph means. You only have to see that this is like, this doesn't have any singularity. But as soon as we change from symmetric distributions to asymmetric distributions, we encounter this kind of singularities. So this is something that we are working on currently. Again, I don't want to get into details. I just want to tell you that by using stable distributions, the phenomena that you get for zero suddenly have a new and more rich results or behaviors. Okay. So the conclusions I would like you to take home is that the Gaussian distribution is just a limiting special case of the stable distribution. I mean, it's a specific case of the whole family of distributions. Then the generalized central limit theorem is the most robust framework for macroscopic reality, in my opinion. And as I told you, extreme events are inherent, not anomalous. So we should take into account the outliers. And these stable distributions are essential for complex physical systems. Shifting from a Gaussian to a Levy paradigm is not just a mathematical exercise. Okay, so I hope that you enjoyed it. So thank you so much for your attention. Does anybody have any questions? No, thank you.
Well, it's a difficult question. So, I mean, how did you think about disordered systems, right? So what would be physically a process where you expect obstacles to have a Levy distributed?
Okay, that's a very good question. Because along my talk, I told you that in nature you encounter many systems that follow stable distributions. But there are two kinds of approaches. Let me go back to this collage. Because in this paper, which is our paper, we did not find a system that follows a stable distribution. Instead, we fabricate a system following stable distributions, right? So there we impose the stable distribution in our systems. But in all the other examples I told you about, there persons or researchers did not put the stable distributions in the systems. Instead, they measured the systems and they found out that systems follow the stable distributions. For example, the financial market, they found that the best fitting distribution is a stable distribution with a stability parameter of 1.40, right? So to answer the question that which physical system will follow in the stable distribution, well, I will say that 99% of the papers talking about stable distributions report measurements, not constructions. So everything in nature follows stable distribution. Is that the question? Or
Yeah, I don't know. I mean, for instance, I would, I have a sample which is a pure crystal, and then I want to put impurities, right?
Yes.
Or by nature, you get impurities in this crystal. So what would be a mechanism for these impurities to have a stable, alpha stable distribution, which would not be normal? And
Thomas, is it not what we saw when we did the Boston protos? That you do the transformation and you get the Anderson model, and then you get this Levy type of organization. It's like the button. And then the Levy appears in the transformation.
I don't remember how the Levy appears.
It's not exactly like the Anderson localization, it's more like a Levy distribution.
This Lloyd
It's
model.
example, I don't know, that's PRL and anything else.
I mean, the rotor is the Lloyd model, which has these Cauchy distributions, right?
Yeah.
¿Es Cauchy o
Okay,
Yes,
yes, yeah.
Okay.
That's true.
Well, a Cauchy
It's also
distribution is a stable distribution. Yeah, I don't know what is the mechanism, but for sure, if we take a piece of quartz and we somehow measure the impurities in that quartz, I will post that you will find a stable distribution following the impurities.
So a piece of
Quartz. Quartz.
quartz.
But what's the mechanism? I don't know. We have to ask God.
I mean, it takes just draw my attention that, I think that that animals and humans do Levy flights is related to optimization, right? So
Yes.
so they did some thinking, some sense or another.
But not only that, it
To
goes
arrive-
by the environment, because
Yes. Also true.
environment is what would make you
There are very two
move
famous
out.
work. One is how one is three maybe. One is being created. Another case is where how the predators hunt. The monkeys try to find out the foods, and what they will do, they will find out the food. They will trap that place for some time. They will eat it, and then they will start looking for. And as soon as they start looking for, they will change their velocity to the group. Okay, they will go with a specific velocity and to a specific place. Now, if you look at the length step distribution of the places they have been trapped, that length step distribution become a power law like a limit. Yeah, that's
But
what.
do you know, so suppose that food is distributed homogeneously but very sparsely,
Yes.
right? So this distribution belongs to the normal class, I would say.
That we imagine. I'm not.
No, because I think it's uniform. Let's say it's uniform. Then there is
Yes. That we imagine.
But it's sparse. But sparse means you have just a long,
Sparse. Yes.
long length scale.
Yes. But that doesn't mean that the distribution will be a power. The distribution could be still large. Sparse, but
That's what I want.
not.
That's what I want. But then you are as an animal who is looking for food, or as a human being, right? You would you then say that the Levy flight is still better
Yes.
in order to
For a
find
human being,
food
there's a paper that is very more interesting.
than
Human
just
being is very
normal
different.
random walk?
Yeah, human being have a specific reason, they say, because human being, for the hunters, basically the still hunters, they don't hunt one specific kind of, they don't search one specific kind of food. They hunt meat, they get corns, corpse and all these things. So that for the diversity of the food consumption in the human society, the people say that's the reason of the Levy flight for the hunters, or the food gatherers, or the foraging in human society. Because I can't just eat chicken, I also need something sweet, something bread, and all these things. So that distribution in general of the food is uniform, but for the diversity of the food collection, the Levy flight come from that. That's what the claim is. However, for the animals, they do not diverge for their food consumption. They are like very monotonous. Still, people find the Levy flight, the landscape distribution to be powerful for the foraging of the animals. And these animals I mostly mean by the predators. Okay. Now, very recently, people started looking at the animals which are not predator, basically for the plant-based diet. That's also Levy flight. The reason people imagine that, because if the predators have to do the Levy flight, those they are eating, they must be doing Levy flight, otherwise why the predators need to do so. And actually they found, in case of at least monkeys, that the movement is Levy flight.
Also, Thomas, last year when Victor was here in Guadalajara, they showed us a paper demonstrating that a Levy flight was better than a random walk for a searching algorithm.
Yeah, but for what kind of searching? That was exactly the question. Because
I think.
Let me just tell you. So you say that the prey also is doing Levy flights?
Yes.
Because they are animals who are looking for food. But then this implies, the same argument implies that the food sources are also distributed.
Not really. That part I really do not understand clearly. Because what they do for this, and this is only for the who have a social structure, right? For example, for spider monkeys, I do not see any paper, and that's like a random. Spider monkeys, they really do not do a living because they live well. But for the example, some of the monkeys who are in a society, and that's not really clear. But what they do, there is a group, and then one or two outsiders, they go out, and the whole group follow them. Now you find out the landscape distribution of each member in the whole place. But there are older members or younger members, they remain close to the center of mass. Right. So that can contribute to the lower part of the distribution. And now those explorers, they go really out. And they have really long tail. They go out, wait there, and the whole community do this kind of small random walk and slowly reach to him. So that can contribute to the Levy flight also. Okay, because if you basically exhaust a food site, you will not look for another food site very nearby because you exhausted enough space. So you really have to move out, and then the explorer they go really far, wait for the community, they come, and then they go far. That way they move unless and until they find out the food resources. That's a 2006 paper. They have a nice YouTube video for that.
Yeah. So you see that it's everywhere in the nature. Okay, well, thank you so much.
Okay.